Welcome to this module on the fundamentals of pulley systems. Today we're going to learn about some common pulley systems, how to identify them, and we are going to learn how to calculate mechanical advantage and velocity ratio in pulley systems. Now, a pulley is a wheel with a groove rim, which a cable or rope or string passes over. It's a very simple machine in that respect. As a simple machine, the pulley acts to change the direction of the applied force. So in this diagram here on the right, you can see that the load is being lifted vertically, but the force is being applied downwards. So in that sense, the force that would be used to lift the load, which would normally be vertically upwards, is now being applied downwards. Now, traditionally, pulleys have been used to achieve significant mechanical advantage and to lift very heavy loads, and we shall see how that's done. Fixed and movable pulleys. Fixed pulleys are permanently attached to a support such as a wall or ceiling, and this prevents these pulleys from changing their position. Movable pulleys, on the other hand, are typically attached to the load, and therefore they move with the load. In other words, as the load is lifted, the pulley moves with it. Mechanical advantage in pulley systems is defined as the ratio between the load lifted and the effort applied to lift the load. In other words, mechanical advantage equals load divided by effort. And we have seen this ratio elsewhere in, for example, the gear trains and the belt drives module, and even in levers. Velocity ratio is defined as the ratio between the distance moved by the effort and the distance moved by the load. Right? Therefore, velocity ratio equals distance moved by effort divided by distance moved by load. Now, there's often a trade-off between the effort needed and the distance moved. In other words, if we wanted to lift a heavier load, we normally trade off the distance that we need to apply on the effort so that we can minimize the actual effort that we apply to lift a heavier load than we would otherwise be able to. Right? So this trade-off between effort and distance is quite commonly seen in a lot of pulley systems. Now we look at the case of a single fixed pulley system. The pulley here simply changes the direction of the force. And therefore, the effort that is applied to lift the load is exactly equal to the load, because all we're doing is changing the direction of the force. And hence, mechanical advantage in this case is equal to 1, because mechanical advantage is load divided by effort, and if both are equal, that ratio is 1. The distance that the effort travels is also the distance that the load is lifted. Hence, velocity ratio is also 1. Now, for a single movable pulley system, the situation is quite different. Now, even though the pulley changes the direction of force here, the force on each side of the pulley must be equal. And because both cables on each side of the pulley are supporting the load equally, the tension force in each cable is equal to half that of the load. Therefore, the effort equals half the load. And if we transpose this equation to load divided by effort, we get 2. And load divided by effort is the mechanical advantage. Hence, mechanical advantage is equal to 2. Now, the distance that the effort travels is twice the distance that the load is lifted. Now, the way to think about it is if the load moves upwards, for example, by 10 centimeters, that means the lengths of the cables on both sides of the pulley must both be reduced by 10 centimeters also, because the pulley would move up by 10 centimeters. And because there are two lengths of 10 centimeters in the cables, that equals to 20 centimeters. And therefore, the distance moved by the effort is twice of that of the load. And if we take the distance moved by the effort divided by the distance moved by the load, that is equal to 2, and therefore the velocity ratio equals 2. Now we can combine fixed and movable pulleys into a compound pulley system, and this can often yield higher mechanical advantage. So in this case, we have a single fixed pulley and a single movable pulley. All right, and you can see that the load is actually supported by essentially two cables, and therefore the tension in each of those two cables is equally spread to support the load, and therefore the tension is half of that of the load in those two cables. Now the blue pulley, however, doesn't actually do much other than to change the direction of the force. Therefore, even though there's that appears to be 3 pulleys in that diagram, there's actually only 2 supporting the load. Hence, mechanical advantage equals load divided by effort. And if the load is 1 and the effort is half, therefore 1 divided by half equals 2. And hence, the mechanical advantage is equals to 2. Now, in another example, we have 2 fixed pulleys and 1 movable pulley. So we have the situation where the cable starts at a fixed attachment to the movable pulley, moves around the fixed pulley, then around the movable pulley, and then around the other fixed pulley. And you'll notice that there's actually only 3 cables supporting the load and the movable pulley. Therefore, mechanical advantage equals load divided by effort, and that's 1 divided by 1/3, which is equals to 3. Now, an easy way to think about it is that if you look at the movable pulley and the load as a single system, it becomes quite apparent, therefore, that this system is being supported by 2 loads, and hence, therefore, the tension in each of them are actually equal to half that of the load. Similarly, if we look at the other example, if we draw a blue box around the system where we have the movable pulley and the load considered as one system, you will see that there are actually only 3 cables that are supporting the system, and therefore the tension in each of those cables is 1/3 that of the load. This other cable obviously on the side is not part of supporting this system, and therefore it doesn't count as a cable that supports the load and movable pulley system. So this blue pulley again serves only to just reverse the direction of the force. So far, what we've been talking about really are ideal cases. There are lossless cases where there's no energy loss, there's no friction, and there's no stretching of the cable, and most importantly, we assume that the weights of the pulleys are 0. In other words, all the pulleys are weightless. Now, in an ideal case, the mechanical advantage exactly equals to the velocity ratio. So in these 4 examples, you can see that the mechanical advantage here is exactly equals to the velocity ratio. So if we take scenario number 2, for example, where the force on the load is 100 newtons, but the effort is 50 newtons. So the mechanical advantage is load divided by effort. That's 100 newtons divided by 50. That gives us a mechanical advantage of 2. Now, if we then look at the distance traveled by the effort, that is 20 centimeters, and compare that to the distance that the load is lifted, which is 10 centimeters, we get the distance of the effort, which is 20, divided by the distance of the load, which is 10. We get velocity ratio of 2. So in this case, the mechanical advantage is the same as the velocity ratio, and that is 2. Similarly, for the other cases, you will see that the mechanical advantage and the velocity ratios are 3 and 4 respectively for the third and fourth example. Now you'll notice that in this diagram there's an indication as to how many cables are actually supporting the loads, and again we can easily determine that by drawing an imaginary box around the system of the movable pulley and the load to quickly identify how many cables are supporting that system. So now we have an opportunity to apply the knowledge that we've learned in a few practice examples. In the first example, we have a diagram with 2 movable pulleys and 1 fixed pulley, and a load with 48 newtons of force applied to it. The question is, what force F is needed to hold the weight still in this scenario? So please attempt this question, and while you do so, pause this video, and when you've worked it out, please resume the video to see the solutions. So the first thing we need to do is draw a box around the movable pulleys and the load so that we can consider them as one system. And once we've done that, it becomes quite apparent that there are 4 cables supporting this system, and therefore each of these cables share 1/4 of the load. Now that we know that therefore the force is 1/4 of the load, which is 48 newtons. Therefore F is 12 newtons, and the answer is A. In the second example, there is an ideal pulley system hanging from a ceiling. There is an unknown load attached to the pulley system, but we know the effort required to hold that load stable is 25 newtons. So please take some time to work through this problem. Pause the video while you work through the problem, and hit resume to see the solutions. Now the first thing we need to do is draw an imaginary box around the movable pulley and load system so that we can consider the movable pulleys and the load as a single system. And once we've done that, it becomes very clear that there are actually 4 cables that are supporting the system with the movable pulleys and the load. Therefore, the effort must be 1/4 of the load. And given that we do know that the effort is 25 newtons, the load therefore must be 4 multiplied by 25, that's 100 newtons, and therefore the answer is C. This brings us to the end of this module. The last 2 questions were taken from the VCE end of year written examinations for systems engineering. I hope you enjoyed this module, and thank you very much for viewing this video.